final topic, which is group actions and the Sylow theorems. Just to give a very broad indication of what the Sylow theorems are about, recall Lagrange's theorem. Which said if a group G was finite, if it had order n, then H a subgroup of G implies that the order of H divides the order of G. It's basically what Lagrange's theorem said. So this, as we were discussing it, and as it came up in the coursework, we were describing this as it places limits on the possibilities for subgroups. You can only have subgroups whose size is a divisor of the size of the group, finite groups. And so that leaves the question of, well, okay, so you can only see subgroups that are divisors of the order of the group, but when can we make a definite positive statement that a group certainly has a subgroup of a certain order? Okay, so the Sylow theorems go some way. We won't look at the precise statements of them yet, because we'll focus on the group actions topic first as a lead up into them. But the Sylow theorems go some way to giving positive results in the direction, if D does divide n, so if you have a divisor of the size of the group, then it's certainly not going to violate Lagrange's theorem if the group has a subgroup of size D. That's allowable by Lagrange's theorem. But Lagrange's theorem doesn't guarantee the existence of such a subgroup. That's important to see. The Sylow theorems will in certain circumstances. So they go some way to giving positive results in the direction that if D divides n, then G has a subgroup of order D. I'll put that thing in quotes because that is certainly not true in general. It's not true for every divisor of the size of the group that the thing necessarily has a subgroup of that size. Your coursework problem was showing that that wasn't the case for certain alternating groups. But for certain types of divisor, and it's going to be related to the prime factorization of the size of the group and so on. Okay. So that's just a kind of broad setting for where we are. But the topic, so the Sylow theorems, they're quite strong in that they make positive statements, they make existence statements about subgroups that a group has to have just based purely on the size of the group. So they are quite powerful. And so we need to develop, it's not surprising then that we need some new concepts, we need a bit of new theory in order to be able to say, in order to be able to prove them. So this brings us on to the idea of group actions. So the group actions is defined at the start of section 14.1 there, but just to say in kind of a vague way what a group action is. So a group G acts on a set X. Now what's this set X? Well, for the moment, given the abstract definition, it's just going to be some set. It's going to be some set that has some kind of connection to whatever's going on in the group. So examples that we'll see are, so for instance, when the group G is a group of symmetries of a certain thing, symmetries of a polygon or something, then the set X might be some kind of labeling of the polygon vertices or some kind of structure that's built on the polygon. Or there's another example that we're going to look at soon where G is a group of 2 by 2 matrices. In 2 by 2 matrices, we know are naturally associated to linear transformations of the plane of the two-dimensional vector space. So in that case, we're going to have the group of 2x2 matrices acting on the set of points in between. So a group G acts on a set X if we can use, so this is just in very vague terms, if we can use the elements G of X to, and let's just say very slapdash, to move around the elements of the set X. Okay, so if you can take an element X from the set and somehow G acts on X to give you another is equal to some Y to give you another element of the set X. Okay, so you very much think of it as a kind of some kind of dynamic process. So just an informal definition. So you pick an element from the group G and you can use it to shift around the elements of X. You take any element X, little x in the set, and then G of X, and this is kind of, you see G acting on X like a function. G acts on X and gives an output Y, which is again another element of the same set. And it does this in a way that respects the group structure. That respects the structure of G. What do we mean by the structure of G? Well, we mean all the properties that G has as a group, which fundamentally comes down to the group operation. So the elements of group G are certain kinds of mathematical object, and there's a natural, meaningful way that we multiply them together. Multiply the group elements together to give other elements. Okay. So now we can see the formal. Now we'll meet the formal definition in section 14.1. Okay. So, and we do this through the language of functions. Okay. So let X be a non-empty set. I mean, you might allow a group to act on the empty set, but there wouldn't be much interest in going on because there's nothing in the empty set. So we'll assume the set X is non-empty. Let X be non-empty and G be a group. Now, there's a slight technicality we bump into straight away, which we'll see in a moment, is that you can define things to act on the left or on the right. And this is kind of somewhat connected to maybe, the idea of commutativity as well, that we have to be careful and distinguish exactly what we mean. It's already something applied here, and it's kind of connected to the normal way we write functions, where you put the function or operator on the left and the thing it's acting on to the right of that, so f of x. Similar kind of idea here. So a left action of G on the set X. Now, the way they have it here is we say it's a map. So the action is a map. So this is the Cartesian product. It's a little bit confusing with the two x's. So this x here is the Cartesian product. A map from the Cartesian product of G and X to X. So this is just a fancy way of saying, that for any pair G and X, where G is an element from G, equal X is an element of X. Remember, that's what the Cartesian product is, just a set of all ordered pairs. Something from the first thing and something from the second thing. So, and this is going into X. So this must send G, the pair G and X, to some other element of X. And okay, I was maybe trying to use another symbol Y for that element, but we just conveniently denote this new element of the set X by the two-letter symbol GX. Okay. Or another way of thinking of it is for any element g from x, we have a function or a map g, it's called that element, and it goes from x to x, and it sends an element, little x, to the element gx. Okay, and that's kind of the way I prefer. This direct product construction is maybe a little bit artificial. This way in the brackets is maybe the way you think about it mostly. So every group element of the group represents a function of the set to itself. It moves the elements of the set around. Okay, you give the group element a little x, and it gives you another element of the set x. Now, not just any old functions. The functions that come out of this have to respect the group structure of G. And this is embodied in two properties. So the action has to satisfy certain properties. And the first property relates to the identity. So the identity element is special. The identity element is special. So it's not surprising to think that the behavior, the function that's associated to the identity element. So this is the identity element E. Remember that's an element of the group G. So we want to associate, or we want to speak about some function from the set X to itself that's kind of naturally associated to the identity element. And what kind of function immediately springs to mind? Which function? And see, we don't know much about the structure of X. All we know is it's just a set. But what kind of special function is there from a set to itself that we might naturally associate with the identity element of a group? Comes in the name. I mean, if I just tell you there's a set X over there, and I want you to talk about a particular function on that set X, well, if you don't know anything else about the set X, the only real specific function you might point to is the identity function. Just the function that simply takes every element from the set and sends it to itself. Quite a boring function. There's nothing much going on about it. There's not a whole lot interesting you can say about it. But it is naturally associated to the identity element of the group. The identity element of the group, after all, is a special element that doesn't change any of the other group elements when you multiply them. So if E of X, I mean, you can almost think of having brackets around the X, except we don't put them down here. But you could indeed put them down. So Gx appears like G of X, and then it's clear G is a function acting with the argument X. So we don't use the brackets by convention. And this is just simply saying that this function associated to the identity element of the group sends any X to itself. So it's the identity function. Okay. I.e., E is associated to the identity function. Identity function on X. As I say, not knowing anything else about the set X, the identity function is the only function you can point to and pick out. Okay, so that's good. It has a nice, meaningful, sensible relation to the identity element from the group for group action. And then the second property relates to really the fundamental idea of what's going on in the group, and that's the group action. Okay. So you think about it here that you imagine you have two elements from the group. So if you take two elements from the group, say a G1 and a G2, okay, if we've got an action, if we've got a left action, that means you've got two functions, G1 sending X to X, and G2 sending X to X. So, you give G1 any little X, it sends it to another element of the set X. You give G2 any element from X, it sends it to another, maybe the same one, but it moves all the elements of X around. So the question here is, what relationship, what connection do these have? To the function that we're going to associate to the product of the two elements. Okay? This, because the essential idea, the essential notion of what's going on in the group is in the group operation. You take any two elements, G1 and G2 from G, and build and form the product G1 times G2. So here's two functions from X to X. Here's another one, which is associated to the product of those two. Now, the group action has to respect the group structure. It has to connect well, mesh well with the group structure in G. So we don't want there to be no connection between these two functions and this function. We want there to be a nice, strong connection between these two functions and this one that connects with and interprets and meshes well with the group operation. Okay? And thinking like that in mind, it almost falls out. This condition almost falls out. So here's this new function from X to X, acting on an argument X from X. So it comes down to thinking, well, what does this value have to look like? And kind of the most natural, even just in terms of what you've written down on the page, kind of most natural thing to choose is the composition of the two functions. So whatever this value is, we're going to insist that it's the same as first acting on the element little x with the function G associated to G2, and then acting on the result of that with the function associated to G1. It falls down quite naturally on the page. I'm almost writing the same string of symbols, but just organized differently. And so just appreciate the different things here. On the left-hand side, we've got the function associated to this group element, G1 times G2. It's a function setting x to x. On the right-hand side, we've got a value of the function G1. And it's the value that it takes on the argument itself, the value that the function G2 takes on x. And it looks sensible, it looks nice. G1, G2 applied to x is G1 applied to G2 applied to x. So that's the second, that's the main second part of the definition of group action. So in other words, we're saying that this function G1, G2, this function, so little x talking about the function as a thing in itself, this function on x to x is equal to the function G1 after G2. Okay? So these objects here aren't so much the group elements, but these objects here are the functions x to x. Okay. So considering these things as functions from x to x, we're saying that this function associated to G1, G2 has to be the composition of these two. Okay. Again, we're just talking about these things in abstract at the moment. It'll maybe become a bit more clear and concrete when we start looking at specific examples. Okay. So just kind of writing that down in a compact sentence, in a compact condition, we say for all G1 and G2 in the group G, the value that the element G1, G2 takes on the element X has to be the value that G1 takes on the value G2 of X. Okay, and this is true for every little x in the set X as well. Okay. So just as we have a very nice natural function associated to the identity element, we've got a very nice natural function associated to the product of two group elements, namely the composition of the individual functions associated to G1, G2. Or in function language, This equation is an equation amongst values in the set X, but in function terms, the function associated to G1, G2 is equal to G1 after G2. And here we have a connection, which is kind of a notational thing, a connection with this idea of the group acting on the left. So agreeing to put the group element on the left of the argument X. That connection with the interpretation of the composition symbol is G1, this composition of functions is G1 after G2. So G2 is applied first and then G1, not the other way around. I mean, it could be that the meaning of this thing was G2 after G1. And lots of students make that error because they're used to reading English from left to right. So we think that this is the first thing, I mean, they've got a 1 against it. This is the first thing and that's the second thing. But really, this is the first function applied, that's the second function applied. Because we have this convention of normally putting the arguments to a function to the right of the function itself. That's just purely arbitrary, it's purely a decision of how to organize your symbols on a page. And in some areas of computer science, sometimes they really explore or they make lots of use of different conventions. So this actual convention of putting the argument after the function name is called postfix. The argument goes after it. There's also prefix, where the argument goes before. Or when you've got binary functions, you can talk about infix notation. The function name goes in between the two arguments. It's a binary function. It takes 2 arguments. But anyway, that's so that's our definition of a group action. So you see underneath that definition 14.1, you say, okay, in this case, you can call X a G set. I mean, that's just a terminology. So X is a set. Calling it a G set means that it's just a set which has some action of G on it. Okay? And trivially, there is always, G can act on any set X with the trivial action. And this isn't particularly interesting. Trivial action defined by G of X equals X all the time. So for every G, an element of G, and for every X, an element of X, G of X is always equal to X. But that's supremely boring. Nothing moves around. Everything does the same thing. Not particularly interesting. So that's the definition. We have the set X of some kind of elements, which in all of the examples, the set X, the elements in the set X will have some kind of connection to the group G. And the elements of the group, you pick up an element of the group, a particular element, little g, and you then got a function in the set X to itself. The group element moves the elements of X around. Okay. So we can look at a couple of examples here that he has. Let's make use of the text here. So 14.1 and 14.2, these are quite natural, easily arising examples. So the first example is the group G is GL2R. So remember, this is the general linear group. It's the set of all 2x2 matrices with real entries where the group operations matrix multiplication. So sorry, it isn't all 2x2 matrices, only those invertible 2x2 matrices. So the group operations multiplications, so the inverse elements are what you know as the inverse matrices. So these are 2x2 matrices with determinant non-zero, so that they're invertible. The set X, and so as I said before, and you'll know from your other studies, 2x2 matrices, n by n matrices are naturally associated to linear transformations of n-dimensional vector space to n-dimensional vector space. So 2x2 matrices are naturally associated to linear transformations, two-dimensional vector space, in other words, R2, two-dimensional real vector space, R2 to itself. Okay, and So we're used to taking a vector, what we think of as a vector, an element of the set X, an element of R2, and multiplying it by a matrix. And so this is just recognizing that that kind of setup that you already know about, taking a column vector X, multiplying it by a matrix with the matrix on the left of the column vector, and that is, in fact, that meets the definition of a group action. Okay? So you take any little x, you multiply it on the left by a. So we're just checking that it satisfies those two conditions. So of course, what's the identity element in this group? The identity element in this group is of course the identity matrix, 2 identity matrix. And of course, you multiply any vector by the identity matrix, of course you get the same vector back again. So this is true that E from the group times a little x gives you the same little x. I, which is the identity from the group, times little v from R2 gives you the same little v. Okay, so it meets condition 1. That it meets condition 2. So what we're talking about there is if we take 2 elements in the group, namely 2 2x2 matrices, we consider the product of them, G1 times G2. So we consider the matrix product, A times B. And we're wondering what's the effect of that by left multiplication on a column vector. Well, then we have this general property. We can consider the column vector as being a matrix as well. So we've got a triple product of matrices, and a general underlying fact, multiplication of matrices is always associative. Okay. So that triple product evaluated like that can also be evaluated like this. You can first multiply little v by b, and then multiply the result by a. But that's exactly that second condition from the group action. The result of applying product of the group elements to the argument little x must be the same as applying group element on the left, G1, to the result of applying group element on the right, 2, which in our case is b, to the x first. Okay. So that's a pre-existing example you already knew about. You just didn't know that it was also this thing called a group action. Okay. Second example, 14.2. This is based on a square. So the set X here is some way of labeling the vertices of a square. Okay, so you have a square. We can associate labels to the vertices: corner 1, corner 2, corner 3, and corner 4. And then we can represent the elements of the dihedral group D4. Remember, D4 is the symmetry group of the square. So the group of rotations of the plane, reflections of the plane, certain axes that are symmetries of the square. It's a group of order 8. And represented as permutations of the vertex labels, you get these 8 elements here. You have the identity element, the permutation that swaps 1 and 3. So that means that's reflection around that diagonal there, because 2 and 4 stay where they are, but 1 and 3 swap. 2, 4 is the reflection around that axis. And then the other these products of 2 cycles, they're the other reflections in the vertical axes. So reflecting in the vertical axis swaps 1 and 2 and swaps 3 and 4. So that's swapping 1 and 2 and swapping 3 and 4 is this one. This reflection swaps 1 and 4 and 2 and 3. It's this one. And the other 3 elements, this one, this one, and this one, those are the 3 non-identity rotations. So rotation by 1 quarter turn, 2 quarter turns, and 3 quarter turns. Okay, so those are all those elements. But clearly, we can kind of reinterpret that picture as thinking of these elements of the group acting on this set of vertex labels. Okay? So you pick up any element from the group, it's a permutation of the 4 symbols. So it naturally has this effect. You don't have to force it, it just naturally has this effect that it moves the elements of the set around. Okay? And it does so in a way exactly in accordance with the definition of the group action that we have. First condition, yes, the identity symmetry just leaves the original square where it is, so it just sends each vertex to itself. Okay, so that's satisfied. The second property really naturally comes up. It's just an associativity of function application to arguments, very much like the previous example. Okay. Yeah, so this is just noting that in general, final paragraph here, in general, if X is any set and G is a subgroup of the group of all permutations on that set, so this is a case in this example here, so this is the generalization of that. The dihedral group D4 represented like this. This isn't all of the permutations of 4 elements, it's only some of them. So we're in this case that we've got a subgroup of the set of permutations of all the elements. Then that will naturally give rise to a group action just under this idea of taking the permutation sigma and just applying it to the argument X. Okay, so at this stage, we'll look at another couple of examples now. But any questions just about the basic definition? I think it is quite a natural idea, and it helps to think of it almost very much in this function definition way. So the idea that the group action is this system where when you pick any element little g from the group, it gives you some kind of function from the set to itself. And those functions, under composition of functions, have this nice gelling with the group operation. Okay, that the function associated to G1 times G2 is exactly the composition of the functions associated to G2 and G1. Okay. And the next two examples are kind of funny when you first see them, because these are self-actions. This is the case where, so you see example 14.3, where you let the set X be G itself. So this is kind of funny because when we defined the idea of a group action, we kind of stressed in our language and we stressed in our notation how the set X is something separate to G. And G has a certain action on the set X, and you think of G over here, X over here, and the two things. So these two examples kind of collapse the notion. So it's, although we stressed and maybe tried to emphasize the fact that X, we should think about it as X as being a different thing to G, actually we never explicitly stated that. So there's nothing to stop us collapsing the two together and say, well, what happens if we consider the set X being G itself? Can a group act on itself? Well, there's a very extremely, it just pops up immediately, it's there already. There's a way for a group to act on itself, just using the group operation. Yeah. So if you try and set this picture up here, where the set X is the group G itself, there's an obvious way to think, well, if I take an element little g from my group, how can I give myself a function associated to that little g that moves the elements of the group around? Well, the obvious way is to think of, so here he's given the notation lambda g. This is the function associated to the group element g, but it's simply the multiplication of g on the left. Yeah. So you pick out a particular element little g, and that's going to move all the elements of the group around by simply multiplying the other elements on the left by the element little g. And the second condition, condition number 2, that the group action had to satisfy, this then just becomes an instance of the associativity law in the group G itself. Okay, so that's naturally immediately satisfied. The second example, which is also a self-action, also a group acting on itself is, one that's maybe not so obvious, but it is a notion that's come up a few times, and indeed it came up in the coursework. This idea of conjugation. Conjugating a group element by another group element is to do this construction written down here as HG inverse. To do something, which is H inverse, to do something else, which is G, and then to do the inverse of the first thing you did, which is H. It's kind of a natural construction. So this example of a group action is again, so G is acting on itself. Well, no, we're looking at, so this is the self-action of G on itself by conjugation, but you can actually set it up for any subgroup H of the group G. So you can talk about a subgroup acting on the whole group itself through conjugation by the elements of the subgroup H. Okay? So the function that's associated to the element little h is this function that moves a group element little g to the possibly different group element hg so to confirm that it is a group action, you want to confirm that it satisfies those two properties, 1 and 2. Certainly, if you think of taking the identity, so the identity from H on G, that's going to be sent to E inverse, which of course will be equal to G, because it's the identity. So it clearly satisfies property 1, which is that EX. Property 1, so this is property 2 here. Property 1 is that EX equals X for all X. So it certainly satisfies property 1, E times G. So in this meaning, E times G is not the left multiplication by E that we had before, but conjugation by E. So EG inverse. But it turns out to be the same G in that case. The second property is for dealing with the product of any two elements. So that's proven here. And so this to prove this just uses a combination of associativity and the property of taking an inverse of a product of two elements. So if we take two elements from the subgroup H, so a H1 and a H2, and we look at the value of the function on the argument G, well, by definition of this thing, we conjugate by the product H1, H2. So we have H1, H2 times G times the inverse of H1, H2. We don't worry about putting brackets around this because we know it's associative, so everything works out. Now here, okay, there's an intermediate step, which is maybe missed out here, but you can say that this is equal to H1, H2G, and, well, what is the inverse of a product of group elements? That should trip off the tongue easily. An inverse of a product is the product of the inverses, but in the opposite order. So the inverse of H1, H2 is exactly H2 inverse, H1 inverse. Okay? But then you're just basically applying associativity. You consider this long product of 5 elements as being this inner product of 3 elements, H2G, H2 inverse, and then multiplied on the left and right by H1 on the left and H1 inverse on the right. Okay, that's just straightforward associativity. But then that is clearly conjugation by H1 of the conjugation by H2 of the argument G. So we are looking at there the application of H1 to the result of applying H2 to G. So that proves that it satisfies property 2. Okay. The third example, yet again, is another example, again, of, well, not quite a self-action here, but here we have an action of the group G, not on itself, but on the set of cosets by a certain subgroup. In particular, this could be an action of G on the quotient group, G by H in the case where the subgroup is normal. But in general, a subgroup won't be normal, but we can still talk about, so this notation curly L, handwriting L, so H, that's the set of left cosets of H. Okay. In the case where H is normal, then that actually forms a group. But otherwise, in general, we can always talk about this action of the group G on that set of left cosets. And again, it's not artificial, it's an entirely naturally defined action. So, okay, we want G to act on LH. So we want to take an element little g, from group G, take a coset of H, a left coset, so that's going to look like an X times H. And we want to imagine little g as a function acting on this argument. So what value is it going to have? Well, we want it to be an action on this set, so we want it to give a value of another left coset, or some left coset. Which one? So which left coset? Well, if you think you want everything to mesh together well with the group structure, and remember that X is an element of the group G as well, so there's really only one choice. The only choice, it's just almost sitting there in front of you, except there's a comma in the way. It's the coset associated to the element G times X. Okay. So again, it's there already. You don't have to artificially construct it. And you can check both conditions. First condition is true just by the properties of the identity, and the second condition will be true. Well, again, it's basically just the idea of associativity coming through. So, the reason that this is true is basically just a consequence of the associativity in G fundamentally, which itself then gives rise to associativity of multiplication of cosets and so on. But essentially, it's just by associativity in G. Okay. It's actually almost perfect. Oh, no, it's Tuesday, so it's just a test. I was going to say it's almost perfectly timed because it's maybe a natural place to stop, just having seen the definition and a number of those key examples. So that's the end of that run of examples. In the second lecture today, we'll start building up a little bit of the theory, and this is going to focus on two things called stabilizers and orbits. So these are two natural ideas that we can associate to the idea of group operation. But even now, it's maybe not hard to see somehow that this is going to go through to the C-log theorems. The C-log theorems, which we haven't looked together at the precise statements of them, although you may have looked ahead in the book. But as we said before, the C-log theorems are going some way to giving Lagrange's theorem in the other direction, asserting the existence of subgroups of a certain size of the group. And it's going to be built on this idea of a group acting on itself through the operation of conjugation. And it's kind of maybe not hard to smell some of that relevance or smell some of that idea that when a group is acting on itself by conjugation, you're studying the group and looking at the number of possible ways that the group can move its own elements around using the group operation. And it's maybe not too much of a stretch to see that that's going to give you some connection about how the number of elements there are relates to the possibilities with the group operation, the possibilities for subgroups in there, based on the number of elements in the group itself, or by extension a little bit, the prime factorization of that number of elements in the group. Prime factorization of the number of elements in the group. Okay. So when I see you later on today, we'll look at these concepts of orbit and stabilizer, and we'll establish some things about it. Okay.